Imagine with the transistor channel model, there's a lot of things that are really interesting. And in particular, you get this interesting connection between basically what is biological channel and the gating mechanism of that, and a transistor channel and the gating mechanism of this device. This turns out, and it turns out at a simple level, you basically have a very similar band structure that you're looking at in both cases. And so this sort of dictates pretty much all the properties you're going to end up seeing in both cases. Now, in the biological structure, what you're going to see is you're going to have some issues due to the just the organic molecules shifting in conformation, which is, but in some sense, what's actually happening in the channel potential sets a lot of that dynamics as well. So all of this tends to fit together, and so you look at this and you think this would be great. The first question you ask is, why wasn't it there? And what you begin to realize is that MOSFET transistors, at least the way we understand them now, really was not something that Hodgkin-Huxley had in the early 50s. You might argue there was a Lillienfeld patent in 1931 that the Bell Labs team in 1947 was trying to make a MOSFET and failed, made a BJT instead. But again, there was only so much of this that was crossing over at the time. So it's not surprising that it would take some time for this to kind of coalesce into a concept. But you can imagine an interesting question to say, imagine that we were with Hodgkin-Huxley in the early 50s. And in so doing, we'd say, okay, well, let's actually try to build a model. And we somehow knew about MOSFETs and subthreshold MOSFET operation. Bit of a stretch, but let's play the conversation out. Because they had a whole bunch of data for basically squid axon. And the question then became, well, what would that actually look like? What does the rest of the dynamics look like? Because I certainly could talk about having two transistors. In this case, I would choose two PFET transistors. I could have chosen NFETs or PFETs. It effectively doesn't make a huge difference, except that it makes a difference on the circuit you build. And I know I'd have a capacitance, and I know I'd have my potentials set up, and I would actually try to set those potentials as such that the difference between EK and ENA are going to be the same voltages that I would see in the Nernst potential between potassium and sodium. So around 140, 150 millivolts. So if you want to say in UT units, which is a good way to think about it, maybe about 6 UT. And you build from there. And you say, all right, well, if that's the case, then what I'm really asking is with all of the dynamics structures, and they did a wonderful job in terms of isolating various currents in Hodgkin-Huxley's original experiments, you say, well, why don't I try to find what would those gating variables be for those particular FETs? Which means I have to kind of invert the voltage current relationship out of the channels into the gating potential and look at that as a function of the membrane voltage. Well, in fact, that's kind of where the research went. There's a much longer discussion in Ethan Farquhar's original papers in 2004 and 2005, which goes into this in great detail, and you sort of see what those elements are. Well, once you see that in its linear and nonlinear forms and dynamics, which was what was done, you can say, well, what kind of circuits would implement those functions? And certainly there's a little bit of creativity of the designer, but you have to get all the nonlinear characteristics, and this was a very, very important aspect. Well, in the original paper, what you end up seeing is actually a very simple bandpass filter for the sodium gating potential that fit Hodgkin-Huxley data quite well. In fact, as well or better than actually their models did. And a similar sort of thing for the potassium channel, building on a number of things both in their data and other data more recently in terms of how we understand the potassium structures. And it turns out that this would give you interesting dynamics, gives you really nice spikes. This was one of many different kind of tuned spikes of elements in a biological range. You could get all sorts of firing, but you also got all of the typical sort of behavior of delay through ramps. You got all of the various steady state and dynamics behaviors, and you could treat this as a true fourth order system. So we had one circuit that handled all of this in one place, and this was really pretty incredible. Because you can actually say, well, is this a circuit model that's designed to be a dense circuit model? And the answer is yes. Is this a circuit model that's designed to be a biological model? Yes. So it's actually both, and in the process there's a lot of things that become very clear in the Hodgkin-Huxley dynamics that come out of actually seeing the basic circuit dynamics that you're working with.